Hello and welcome to 18th lecture in 19th chapter of our comprehensive course on AI, machine learning and DS. In the previous lecture, last thing which we did was this real life data science example. And what we said is that suppose my company has customers across entire India and I have divided my business operations into various regions like Northern India, Southern India, Western India and Eastern India. And I want to study some particular characteristic of my customers using the data of those customers. Say I want to study customer retention rate, but I can study any other characteristic and I want to build a predictive model. So what we do at that time, that I told you that you take your entire all the customers as one population, from which you make four samples: one sample of North India, one sample of East India, one sample of West India, and one sample from South India, right? And then each sample will be quite different from each other because they have their local factors which are giving them some particular nature of the data, and therefore each sample may even not be normal also. But still, when I find the customer retention rate and then I find the mean customer retention rate, then I say that that is the mean customer retention rate of my business operations in India. I don't have to bother about whether specifying for North, East, West, and South separately. Okay, so what allows me that to do that? Okay, so there is a business which collects monthly data on customer retention rate across regions. The retention rate in various regions may follow non-normal distribution due to some local market factors. So there may be some exponential distribution like this black colored, or maybe uniform distribution like this, okay, where my cursor is on the right side of the screen here, okay. But that means any this kind of distribution may be. But how do I find aggregated customer retention rate? Then it just says that you just aggregate customer retention rate and calculate the mean retention rate and find the confidence interval. Now this looks very simple, that okay, I will find the mean retention rate for this, retention rate for this, retention rate for this, and retention rate for North, East, West, South, and then I will add them, aggregate them, and divide by 4, that is find the mean. And that I will say that that represents my entire business. So that means that represents my entire all 4 regions. Okay, now the question is that what is the guarantee? What gives the guarantee that the behavior of each region, the mean of each region, North, East, South, West, and the behavior of my entire population, that is the business as a whole, will exactly be such that I can aggregate without compromising on any scientific method or assumption, right? So then central limit theorem gives that ability. If central limit theorem would not be there, then in that case it would be difficult to aggregate different samples like that. Now that has many more applications also. For example, here the beauty of central limit theorem, right? So here it is said that the central limit theorem ensures that the average performance matrix, for example root mean square or accuracy or even precision or recall, that is true positive rate, false positive rate, all those things, they from cross validation approximate the true population performance. Now what is this cross validation? So for that I have given this some diagrams, right? See how we do data science. Suppose this is one entire data in which first columns are the feature columns and the last one column, that is target column. So first of all I divide into X and Y. X is called my feature matrix and Y, small y, that is called my target vector, right? Then this X whole feature matrix, I divide 80% of X into X train and 20% of X into X test. Now the ratio may be 80-20 or 70-30, but in short the majority portion is kept in train and the minority portion is kept in test, right? And then this is Y train and similarly this is Y test. So that means this is also divided into 80-20 parts and this is also divided into 80-20 parts. So first you divide feature and target from each other, that is a kind of vertical division. One column is separated from rest of the data set, and then each two which are generated like this here, they are horizontally split so that each is divided into X train and X test and similarly Y train and Y test. Now these train variables, both X train and Y train, they are directly fed to my algorithm. So if I am using random forest, then random forest algorithm is allowed to look at X train and Y train. So that means it is allowed to look at all features and it is also allowed to look at corresponding labels. For example, this is a classification task and I want to do customer churn. So these are the various features of the customer and this says yes or no. Yes or no means customer whether he will churn or not churn. So for 80% of the data, say I have data of 1000 customers, then 800 rows, I allow my random forest algorithm to see both the features as well as the target variable. So that means the algorithm learns the pattern that okay, these kind of features are there, then I get yes. this kind of features are there, then again I get yes. So maybe this and this, from which I will try to find out some pattern. This kind of features are there, then I get no, that customer will not churn. Okay, this kind of feature, again yes. So maybe first, second, and then fourth, all are giving me yes, that customer will churn. So from there I will try to find some pattern. Then this kind of feature are there, fifth column, no. So that means second and third and fifth row, they give no. So maybe they have some different pattern which cause the customer not to churn. Okay, so after passing through all 800 observations, my algorithm, that is after passing through X train and looking at corresponding labels in the Y train, my algorithm learns some pattern, that which is called trained algorithm, or that is itself called a machine learning model. Now then, we use that machine learning model only on X test. At that time, we don't show it this Y test. Okay, that means the labels are not shown, but labels we have. Okay, so we know what are the actual behavior of these customers. Say this 2000 customers or 200 customers. We know that some have churned, some have not churned, but we hide that labels from the trained model, and we ask the model to predict this thing, whether the customer will churn or he will not churn, right? So at that time, you will get here one more similar column. These are three here shown, similar three, or that is if there are 200 rows, then 200 rows of Y predicted, and then how good my model is, that is decided by Y difference between Y predicted and Y test. And there we have seen that two kinds of difference we take. One is absolute difference, because positive errors and negative errors should not cancel it, so we take a modulus. And second is the squared mean squared difference. So that is a different thing, that but somehow we find a difference between predicted value by this model and the actual level, which I did not show to my model, but my model try to predict this for these 200 rows, right? And then the difference between them, that was fed to my machine learning models, right? Now the difference between them, that gives, sorry, that is fed is wrong, that gives the accuracy of my machine learning model. Okay, how good is the fit of my model? This is also showing the same thing once again, just for the sake of revision. So these are my feature columns, and therefore this whole white portion, that is called feature matrix, because there will be horizontal lines also. So it will be a 2 by not 2 by, but say these are 4 columns, and these are suppose 1000 rows, then it will be 1000 by 4 matrix, right? Okay, and this will be my test. So I will first isolate test, then I will split the entire thing into two parts, so that train is also splitted into two parts, X train and X test. Sorry, X is also splitted into two parts, X train and X test, and Y is also splitted into two parts. Y is here, this purple shaded. So Y train and Y test, and then this is my training portion. So I allow my algorithm to look at my trained data and both response variable or the label. Okay, and from that my trained variable has given me some models. Now that model is the same model is used from my X test, and it gives me some prediction. So these are my actual values which I had hidden from my model during the when it was trying to predict on X test. Okay, so I don't want to show it, but I have the actual value, and these are my prediction which the model, after learning the pattern from the trained data, the model has now become expert in predicting pattern. So it will predict its own values for that Y test. That is this Y test. That will call Y predict, Y pred, and why the difference between Y pred and Y test, that will lead to evaluation, and the evaluation results are then displayed, that 84% accuracy or this much precision, this much recall, and all that. This is the basic principle, whether you are doing regression or whether you are doing classification. The only thing which differs is what you are predicting. If you are doing regression, then you are predicting a continuous variable. For example, what will be the salary of the person based on his education, qualification, seniority, and so on. Okay, that is the prediction of some value, that the salary will be $1,500 per month, or maybe $3,000 per month, like whatever. And otherwise, that is called regression. But otherwise, there is other called classification. That these are the behavior of these are the traits of my customer. The customer's age is this much. He is associated with how many years with my firm for last how many years. Last year, when did last he visited my portal? That is called his recency value. Then how many times in last 6 months did he visit my portal? That is called frequency value. And how much does he buy overall in 6 months? Because sometimes the customer may visit many times, but his total purchase is hardly maybe $5. So that type of customer is clearly buying from somewhere else also. Okay, so that is called recency, frequency, and monetary value of my customer, plus other traits, maybe his age and maybe his gender and all that. And from that, I try to predict whether my customer is likely to churn or not churn. So at that time, here what I am predicting, that will be not some number, but that will be a class, that yes or no. Okay, but that is a different thing, and at that time the process is called classification. But may it be regression, may it be classification, the basic process remains the same as I have done in this diagram. Okay, full data set, divide vertically, features and target you separate out, then divide features X train and Y train separately. Similarly, X traits and Y tests separately in the region. So that is divide this into 80-20 ratio, 800 rows and 200 rows, and similarly divide this outcome variable also into 80-20 ratio or 800 rows and 200 rows. Use these entire 800 rows, that is the train, X train and Y train, to let my algorithm learn some patterns, and then that learned pattern, the algorithm which is trained, that is called model. That model is allowed to visualize only X test but not Y test, and it is asked to predict that similar Y test, Y predict, and then the difference between Y test and Y predict, that will give me the accuracy of my model, right? So that process remains the same whether you are doing regression or whether you are doing classification. Now there, what is this? Now here it says that C.L.T ensures that the average performance matrix, whether you are finding root mean squared error or whether you are finding accuracy or whether you are finding precision or recall, for cross validation approximate the true population performance. Now what is that cross validation? So this is the basic process, but sometimes we make this process even more robust. So what we do is, this is my suppose these are my test data set, okay? So that is the 20%. So think of it as vertically to match with this diagram, okay? So that means this is this blue colored boxes. They are 4. So that is each is 200 observations. So these are total 800 observations that are here. This green 800 observations of X tree, right? And this is my X test. These 200 observations. Now, if I just use say last 800 observations as my training set, last 800 or say first 800. Suppose I'm counting first from this side. So first 800 I use as my training set, and last 800 I'm using as my testing set. Then someone may say that you are not capturing all the pattern, because who knows that some pattern is also there in this. So what is the better way of doing that? In one set of training, I allow my algorithm to pass through this train set at least 5 to 10 times, say 5 times, and in first set of training, take first 800 as the train and last 200 as the test. So from right to left, I am taking the first 800. Each blue box is equal to 200, and each orange box is also equal to 200. So first 800 as a train set, and next last 200 as a test set. But next time you take slightly different. Say only first 600 as the train set. Then there is a test set somewhere here, that is 200 rows, and the remaining rows you again take as a train set. Okay. So these are first 600, then 600 to 800 rows which were earlier forming train data are now forming test data, and 800 to 1000 rows which were earlier forming test data are now forming my train data. So that means what I am doing is I am just reshuffling rows. So these rows about which I had the fear that maybe these rows are also having some pattern, and if I am using only these rows, then the pattern which is there in this row, there will never be captured during the training. So now I am using these rows also in the training. Then next time I do even different thing. I use only first 400 and last 400 for training, and the intermediate 200 that I use as test. Okay. So in short, I slice my this data frame in a different horizontal manner, such that first 800 and last 200, then first 600 in and last 200, that makes the train set. First 400 and the last 400, that makes the train set of 800. First 200 and the last 600, that makes the train set, and the last 800, that makes the train set, and the top or the first 200, that makes the test set. So that means this whole diagram would be inverted sort of, where this first 3 here up to this, that will make the test set, and the rest of the thing they will make the train set. I hope you are getting the logic, right? That instead of taking only few for training and rest for testing, this will ensure that each of the 1000 rows are used for training somewhere and somewhere. Here first 800 are used, here first 600 and last 200 are used, here first 400 and last 400 are used, here first 200 and last 600 are used, and here first 800 are used. So that means you are taking different train sets from same 1000 observations and so on. And whatever performance metrics come, whatever model come, then you take the best out of or the average of performance. Okay, so that means if this gives accuracy 91%, this gives accuracy 92.5%, this gives accuracy 93%, this gives 94%, and this gives 89%, then the sum of all that divided by 5, that one will be the accuracy which the model will show. And you don't have to do anything. That means you don't have to mentally or take a pen and paper and find the average. You just have to, that algorithm will itself do. You just have to specify during the training process that number of folds is equal to 5. So then this is called k-fold cross validation. But why this average performance of 5 folds is the correct behavior of my entire this data set? What guarantees that this average performance is the correct behavior of my entire data set? Then the central limit theorem guarantees that. So now you read this sentence, then you will understand. C.L.T ensures that the average performance matrix from cross validation, cross validated folds, these are cross validated folds, then average performance matrix of them that approximate the true population performance, right? Similarly, another importance of this central limit theorem is here, that bagging and bootstrapping. Now, what is this bagging and bootstrapping? In this data science, there will come something called decision tree. Okay, so I'm showing you what kind of decision tree you will see. For example, this is one example of decision tree for whether or not credit or loan should be granted to a customer who has come to your finance company. A very simple, the decision is never so simple, but just a simple decision tree. This each is called a node of decision tree. So this is a node, this is a node, this is a node, and so on. While these last nodes, after which there are no further arrows, so that is called leaf node. They are the leaf. So this structure is like inverted tree, okay, where this is the root node, inverted tree. So a tree whose root is at the top and whose leaves or branches are next and whose leaves are at the bottom. Okay, so that is called decision tree. And at each stage of decision tree, some decision is taken. For example, a new customer has approached you and you are the officer who is deciding that whether or not you want to give the loan. Okay, now it is a small loan. So if age, first thing, what is the age of the customer? And suppose there the entire sample of 1,000 customer is divided into three parts. If the customer is young, or if the customer is middle aged, or is the customer senior. If he is young, further scrutiny would be required, because say young person is still studying, so he may not be able to afford a credit, right? And similarly, if he is senior, then also further scrutiny is required, because a senior person, if he wants to have the credit, then also maybe he has retired, so he has no income or limited income pension. So you want to first check something about him, then only you will give the loan. But if it is middle aged, say it's around 30 to maybe 45, then obviously he must be engaged in some activity, economical activity, and therefore this is a small personal loan of say 25,000 rupees. So you will say immediately that age group is favorable, so give him the loan. Okay. Now what about these two? If he is student, then you check. If he is young, then check if he is student. If he is student, then don't give the loan, because suppose in the country at present the student loan is having a big crisis and there is going to be bubble in the student loan. That is what suppose the what you call economists have warned, right? So you will not give the loan if he is a student. But if if he is not a student, then don't give him a loan. Okay, that means he is young and he is not studying also. So that means he would mostly use the money for some say luxury items like buying a mobile or something. But don't give the loan. But if he is young and if he is a student, then give him the loan. So give yes. Because from student you can get certain things as a collateral. Many financial institutions, if you know, they are not good institutions, they are not ethical practice, but there are private financiers also. What they will do is, if this is a postgraduate student, then they will take the graduation mark sheet as the collateral, right? Now it is clear that when the student passes the post graduation and at that time he wants to in the job market, then he will require his original graduation mark sheet, without which he will not be accepted in the job job market, right? So at that time the person who is financer, he has a leverage and he can say that if you don't repay the loan, then I will not give you your original mark sheet. As I said, that is completely unethical, but it is done. So student, suppose the policy is that, then yes, give him 25,000 or so, small loan is fine. Okay. Now about that senior citizen. So senior citizen is normally living on a pension or something. So now how to know that whether or not he should be granted loan or not? So check his credit rating. Okay, fair. Now fair will be actually not, but suppose here it is poor. So poor credit rating, then don't give loan. That is the person has defaulted on maybe 2-3 loans in past or so, or his credit score is very low. Okay. But if his credit rating is excellent, then yes, give him the loan. Okay. So that is how these decisions are taken. And there are algorithms which can mimic this whole process. That algorithms are called decision tree. However, there are certain problems with this decision tree, and we are going to study this decision tree in much detail. At that time, we are going to see these problems also. So as a result, what we do is we don't use a single decision tree, but we use an entire forest. That is a collection of 1,000 or 10,000 trees together. Okay, so that collection, that is called random forest. That algorithm is named random forest. So that algorithm type is called ensemble. Its pronunciation is ensemble, but its spelling is ensemble, ENSEMBLE, but it is pronounced ensemble. So what is an ensemble? An ensemble is collection of several such decision trees, thousands of such decision trees. Okay, now you can imagine how complicated it will be, but such algorithms have been made. Okay, so random forest is one such algorithm. But then again, the question is how does one calculate the final result? So the final result is found by again average aggregation. So if this is one of those thousands, then whatever value is given, suppose here we are predicting whether the loan should be given or not, yes or no. So that is a classification example. But instead of that, suppose we are predicting some number, right? So suppose one algorithm has predicted a number and some error came. that error is 80%. Now next tree also predicts 84%. Some other tree is predicting 74%. Some other tree predicts with 90% accuracy. And there are thousands of such trees. Then what will be the accuracy of random forest? Or when the random forest algorithm actually works and shows us some accuracy in the Jupyter notebook, which accuracy it is showing? Then it is showing the mean accuracy of all these thousands of trees. Okay, so that means that it shows aggregated value of error or aggregated value of accuracy. But again, the question is, can we take such simple mean every time? Then yes, we can take, and that is guaranteed by central limit theorem. That there is, because that process is also just like that population and sample. You should understand that from a population, you take small samples, right? And then you find accuracy for each sample and find average, and that you call the accuracy for that model. But instead of that, here now you are not taking samples. Maybe you are taking the whole, you are given a sample, but on that sample, you are using one tree, second tree, third tree, fourth tree, thousand trees, and then whatever answer you are getting, that you are taking the mean of it. Okay, so such thing is allowed because sample all these different trees, whatever the result they give, they are also distributed in a normal manner like this, irrespective of original distribution. So then this is one important thing, bagging and bootstrapping. This process is itself called bagging. What is bagging? So here I have shown somewhere. Yeah, this is called bagging. Now in that, random forest is an example of bagging algorithm. Okay, so what we do is, this is my entire training set. That is this kind of training set. But I don't feed entire training set to one tree. Suppose I have 1 million data points. Okay, and I have 1,000 trees in my random forest algorithm. So I can easily divide 1 million data points into set of say 10,000, 10,000, 10,000, 10,000, and so on. So that is one subset, another subset, another subset, another subset. Similarly, in the test set also, that 10,000, 10,000, 10,000, all are Y trained. Okay, so Y train, X train 1, X train 2, X train 3, X train 4 up to X train 1000. And similarly, Y train 1, Y train 2, Y train 3 up to Y train 1000. And those X train 1 and Y train 1 are used for with one random forest. Okay, one decision tree. Okay, then next X train and Y train are used, X train 2 and Y train 2, they are used with next decision tree. Then the last 1000, X train 1000 and Y train 1000, they are used for training the 1000th decision tree, and all the predictions are gathered. Okay, and finally these predictions are aggregated. That is called the prediction given by the random forest algorithm. So we don't see the prediction of each tree. What we get in our Jupyter notebook after executing random forest is directly this prediction. But what is the guarantee that this prediction is the same as the prediction that would have been if I do all 1 million observation directly in one go? And that means if I take my entire population in one go, X train and Y train, and then X test and Y test, and find a model, and whatever accuracy will come, what is the guarantee that if I divide my entire that population into subset of 10,000 row, 10,000 row, 10,000 row, and 1,000 subset, I make 1,000 such decision trees, I find the prediction for those 1,000 and then find the aggregation. Maybe I take the mean if it is a number, or if it is a class, say whether the person will churn or not, then I will do by majority, that is voting is done. So total there are 1,000. If 800 have given that the person will churn and 200 have given that the person will not churn, then the random forest algorithm will finally give you that okay, the person will churn, because majority says that the person will churn. So for classification, voting is done at this level, and for regression, averaging is done. But what is the guarantee that that aggregated value correctly reflects the same behavior as would be the behavior of entire population of million rows, which I would have directly divided into train and test set? Then central limit theorem guarantees that. Okay, so this is that second thing. Don't worry at all, because we have to do this discussion about bagging and boosting once again in much detail, because the two strong pillar algorithms for prediction are random forest and XGBoost. So one is bagging, random forest is bagging type algorithm, and another is boosting type algorithm. So at that time we will do a lot of discussion of that. But my habit is that whenever even a single sentence is there, I don't let it read it sentence and just tell it that you will learn it later on. Okay, wherever that sentence is, that at least you should get some rough idea about what that bagging is and where the central limit theorem is coming. Similarly, prediction from a large language model like neural network can be aggregated and smoothed by leveraging central limit theorem, improving the robustness. So even our today's famous large language models, maybe our ChatGPT, etc., they actually take the data points in sometimes batches, okay, for reducing the training costs. So then what is the guarantee? Batches is just like this, that you are dividing your data set into subsets and you are training on each subset, and then you are finding the average or voting, whatever you are doing based on that, but only thing is their random forest decision tree was each algorithm. Here each algorithm is a neural network, but that is fine. But there also you can use such aggregation and find the average, and that correctly represents your population because of central limit theorem. Okay, so this is one thing. Key takeaways from central limit theorem. There I will go very quickly because most of the discussion is done already. C.L.T applies to data from almost any data distribution. So whether your original data distribution is Gaussian or uniform or exponential or any other distribution, it will apply to almost word is written because we know heavy tail distribution like Cauchy distribution, then C.L.T will not apply. Even highly scaled, skewed or irregular distribution will yield normal means, normal sample means, which gives sufficient sample size. Okay. Then second point about this is sample size matters because you can take these multiple samples, but each sample should have at least 30 or more data points for better adherence to this central limit theorem. Then central limit theorem is the foundation of modern statistics. Okay, and practically for confidence interval in the surveys to algorithm comparison in machine learning, everywhere central limit theorem is found some place. Okay, now we want to do some practical applications of central limit theorem. One is confidence interval construction, one is hypothesis testing, one is quality control in manufacturing, one is data sampling in surveys, one is algorithm performance evaluation. You can see how versatile this is, and this time we will do it by actual coding and plotting so that you will understand that yes, this is how central limit theorem is useful, right? But that we will start in the next lecture. So thank you and see you in the next lecture.